Hello, welcome to the first of a new podcast series that looks at all things digital platform for leakage analytics, or the DPLA. Over the next few months, we'll explore how data, analytics, and technologies are shaping the future of the Cadent gas distribution network. Today, we're focusing on machine learning modelling for gas leak detection, how it's transforming the industry, and how it can foster environmental and customer benefits across the gas sector. We're joined by two experts to shed light on the work being done and the exciting developments on the horizon. I'm Katie Green from Guidehouse, and I'll be hosting today's discussion. Joining me are Chris Rison from Cadent, who will talk about the business interest and benefits of these innovations, and Rubab Atwal from Guidehouse, who will bring us up to speed on the technical side of machine learning and modelling in methane leak detection. So let's dive in. And we'll just start at the beginning. So, Chris, why do pipes leak and why is it such a problem?
Well, the first thing to say about the pipes, I think, is that they provide a huge amount of energy that we depend on in our lives in the UK for businesses, for heating homes, and they've done us extremely well. So some of them are leaking, but actually these pipes have sometimes been in commission for over 100 years. They've served us really well, keeping us warm, keeping our economy powered. And actually, yes, we do need to think about how we monitor them going forwards. And there's opportunities with new technologies to do that better than before. But why do they leak? Well, they sometimes get damaged, but the main reason is actually that some of the metallic pipes are so old that actually they've just deteriorated over time in the ground, with vibration of streets above, for instance, causing often quite small but collectively important leaks. This matters because every little bit of gas that leaks out of the network is a potential risk, and it's costing someone somewhere money because obviously gas isn't for free. So there's lots of benefits to doing this, and we want to tackle the approximately 5% of gas that's methane emissions. Approximately 5% of UK methane emissions is from leaks from gas networks, which works out as about 1% of UK greenhouse gas emissions. So if we can tackle this really well, it's really meaningful for the greenhouse gas in the UK.
Okay, yeah, so definitely a big problem worth solving. And how will the digital platform for leakage analytics help with that?
It's going to help a lot, actually, because it's a very strategic piece of work that reaches right across the distribution network. So the key objective is to move with modern technology from a world where we've estimated emissions, which we've done for 20 or more years, to a place where we can actually measure and observe emissions from right across the network, be those the pipelines, and I think we're going to talk most about that today, but also above ground sites and distribution mains and services. We want to get away from that estimate because whilst estimates are useful, they don't tell us what we should do, in what order, or where we need to target. And the key benefit of DPLA is it will give us that insight, which means we can make much better decisions. And those better decisions means we will be spending our customers' money more wisely, making much more accelerated progress, and avoiding some of the kind of reactive, kind of disruptive practices that we've actually got quite used to. So we can cut some of that out. So there's lots to go at.
Amazing. And so one of those innovative technologies that you're harnessing for this project is machine learning, and specifically probabilistic modelling. So Rubab, could you tell us exactly what is probabilistic modelling and how is it being applied to detect methane leaks in the gas distribution networks?
Yes. So probabilistic modeling is a mathematical framework where you basically use probability distributions to represent uncertain systems. So instead of using fixed values for variables like pressure, flow rates, leak volumes, leak size, you represent them with you treat them as random variables and then represent them as probability distributions, each with an associated likelihood. the probabilistic modeling framework that we have here is basically being applied to gas networks. And the reason for that is because in gas networks, due to the sensor data and the noise within that data, as well as some faulty sensors in some places, leak detection is inherently quite uncertain. So this framework kind of ensures that we are being able to model the leak location, the leak size, as well as leak detection in the resolution that we want. The output of this probabilistic modeling approach isn't just a binary response. It isn't just a yes or no. It's basically the distribution or like a probability map that tells you how confident we are about the leak being present in all of the given locations. So I think that gives you a brief overview of how we're using probabilistic modeling in DPLA.
Yeah, and it sounds really useful because, it gives you that continuous overview of what's happening in the pipes, where there might be leaks. So that's really useful as well. Could you go into a little bit more detail of like how we've developed these models in practice, how they work, what data sets are used, and how they've been developed?
Yeah, for sure. So just to walk through the whole process of probabilistic modeling, we start with the digital representation of the network. And I know that it sounds simple, but it's really not. I think it was definitely one of the biggest challenges we've had. The reason is that when you look at a network, and even when you try to get segmented, there aren't any two segments that are alike. And each segment has different types of assets. And what this required was for us to make a unified representation of this data where we could query it and store it consistently. We had to go quite a lot of, it required a lot of back and forth between data owners as well as data engineers to store this data, to understand this data. And I think that even as a developer, I couldn't really code in isolation. I had to understand how these assets behave, how the pressure and flows are within each segment, understanding what each asset means. And I think that once we had this unified representation, we then moved on to simulating the hydraulic data for each segment. Each segment of network, we were basically producing pressures and flows, which served as training data. And the reason is because of this structure, we could induce leaks and basically have pressures and flows for as many leak locations as we wanted, and whatever leak size we wanted with the resolution we wanted. So once you have this data, you train it you use it to train the models that we use. So the framework that we have for probabilistic modeling is a Bayesian inference with an autoencoder. The autoencoder is basically mapping the pressures and flows in each segment, in each leak scenario, to the network structure, the different pipes, and it's compressing the data size as well, which is making Bayesian inference possible in real time. And once this is done, we use sensor data to then test each segment that has been trained. The output of this, like I mentioned, is a probability map. So you have different probability values on a map, and you can use that to check what the confidence is or how confident we are about a leak being present in that location. We can set up a threshold or use statistical tests to make a more defined decision on whether we think a leak exists or not, what the leak size is, what the leak size is, the distance of the leak from the start of the pipe. And I think that should give you a good overview of
Yeah,
doing.
that's a really good overview. And, I can tell that it's taken a lot of work, a lot of collaboration between the technical development team and the experts within the gas distribution network who know the pipes and the network inside out. And I really relate to what you're saying about the data as well. It's a really classic kind of problem when I'm trying to apply machine learning solutions to real world data, is having to sort all that out
Yeah.
before you can really get started. Could you just briefly talk about what results you've got from the model, like how we've tested it, and what that's looked like?
So until now, we've been looking at each segment, and the goal is that basically by the end of the project, we would cover each segment. And we started off with the high pressure network, and started with generating data or for leaks that could exist on this high pressure segment. The results from it were quite positive because we realized that with a sufficient number of samples or sensor data, we were able to model the true nature of that segment, and then we had a good probability distribution over where the leaks actually existed. So it's been a test. The testing that we performed has been a mix of both, like looking at prior leaks as well as looking at synthetic leaks. And in both cases, we've had over 70% of leaks being labeled as true positives, and I think that's really good.
If I could just jump in there, because I remember that stage of the project, and I remember talking to my colleagues within Cadent about known leaks from the past on our network and selecting them. And we knew we were basically setting you guys a test. You'd worked hard to, by the way, you said, this sounds simple, but it isn't. It doesn't sound simple at all. Bayesian inference and probabilistic modeling and structuring the data. It blows my mind, actually, what you guys have had to overcome to innovate with these probabilistic pressure-driven models. Because, of course, we don't have the flow data, but we were really, really impressed at that point in the project's timeline where we'd set you a section of the East Anglia network where we knew in a particular point of, I think it was the year 2018, there had been a leak, a significant leak. I think it was a damage on a standpipe that had got called in as a PRE in December, I think it was. And you'd found it about 10 days before we recognise it happened. It was a huge validation of the work you'd done, and it was like a penny drop moment for the project. Actually, I thought that, so cracking.
Yeah, I agree. I think one of the biggest learnings has been that based on how we're modeling and when we start testing, we can, based on the probability distributions, we can understand how well the model is actually understanding the network behavior and whether or not we need to add more leaks, more simulated data to make it better. But yeah, I'd agree. I think that that probability map across a given time period really shows how well we're able to detect these patterns.
Yeah, and gives a lot of confidence in the model, knowing that the model's working and accurately detecting those leaks. And so, Chris, you said you mentioned that the model detected that leak about 10 days before it was reported. How much of a benefit would that be to you guys as a business, having that ability to detect leaks so early?
So I think it can be a really important part of how we safely and efficiently operate the network. At the moment, we don't have a way of identifying those kind of events other than customers or potentially one of our operatives, but there's a lot more customers out there picking up the phone and ringing the 0800 number to tell us that they can smell gas. And I think for the modelling of high and intermediate pressure pipelines, it effectively promises us this kind of early warning system to tell us what may or may not have happened, but give us a good timely update because it's near real time as a model. So the key benefit for me is timeliness and localizing what's going on. So that gives us a good start to say, right, do we respond to these scenarios? What are the right conditions for us to respond? And the benefits are huge. I mean, we all want to keep people safe and warm whilst protecting the planet. That's what Cadent does. That's what the gas distribution networks do. So if we can keep the gas in the pipelines, not waste any, not harm the environment, not have the kind of risks that could go about from these pressure tiers, as you know, are very scary risks. So an early warning system wrapped around that pressure tier is well worth having.
Yeah, and that's so interesting, like, because those obviously the pressures in those pipes are very high, so those leaks may be quite big. So the potential to save emissions and really increase safety is really amazing. Especially, I know a lot of your asset base is quite rural as well, or not around where customers might detect it in good time. If it's in the middle of nowhere, is a customer going to call it in? Have there been any challenges? I know Rubab mentioned, the data challenges associated with the technical development. Have you seen any? What do you think has been the biggest challenge from more of a business perspective in the development of the modelling solution?
I think the scale of the ambition of this whole project to understand emissions and face into them rather than kind of bury your head in the sand and wish they weren't there. The cultural challenge for that to the whole industry is huge. So within the organisation and I suspect the other gas networks feel pretty similar. That's hard for us because we're not necessarily used to having that information, to knowing what's the right way to respond. Where do you draw the line about responses? Have you got the right skills, the right resources? It challenges your processes. All of that happens within the organisation, and we're working through those types of questions. And then outside of the organisation, we've got an economic regulator, crucial kind of part of the industry, and they've got the same challenges and questions. What's right for them to do? They've got to protect customers from a commercial point of view, but equally customers' safety matters and the environment matters. So where do you draw the line? It's hard for Ofgem, and likewise for the HSE. A lot of these changes to the industry that technology and big data make possible, it sort of flies in the face of many decades old regulation, which never anticipated this kind of transparency about what's happening and when in real time and, vast data sets. So how do you sensibly respond to that in a world where we've got so much data about what's going on? You can't respond to everything. So you have to make a well-justified, and you have to think that through about, well, what do you do? When do you do it? How quickly do you do it? How do you resource that? And all of that fundamental change to the industry and the culture and the mindset to face into that rather than face away from it is super tough, to be honest. We're not through it yet. It's a sort of a daily challenge, and it's iterative rather than sort of ones and zeros. But it's very exciting and it feels like the right thing to do.
Yeah, for sure. And that's really interesting. So it's basically a kind of managing that big sea change, innovation, technological implementation across a wide range of stakeholders, all with different kind of priorities and ideas. So do you see any more benefits to the solution, less from a business perspective, but more from a wider stakeholder, customer, regulator standpoint? How do you think we can best get all those parties fully on board?
There are bigger benefits, yes, Katie. I think that the key one, back to the objective of the project, it's about efficiently reducing emissions. And emissions, of course, means wasted money, it means environmental harm, and it could mean serious risk. So it's about effectively and efficiently reducing all those things in ways that we've sort of never done before. So we should see a small help to bills. We should see reducing our risk on the network by better understanding. We should see less reactive works and more planned and proactive pieces of work and investment to get ahead of asset problems. And all of those things are what our customers and our regulators tell us they want us to be worrying about and planning for and making happen. So all those benefits are there.
Yeah. And as we've talked about a bit, the probabilistic model that we've been developing is a real key way that we can achieve some of those benefits. So Rubab, from your perspective as a developer, what do you think has made or makes the DPLA project so innovative? And what are the next steps that people at Cadent should be looking out for?
As a developer, I know that this is probably the first time that we're applying a probabilistic modeling framework to a gas network, which is really exciting. But while I've been working through the development of that entire end-to-end process, the most exciting thing has been that I've had to research or read about every component of it. So I don't think that anything that we've done, including all the smaller steps as well, has been done before. We've had to think around it a lot. Even the digital representation as well. I think that's really cool. Like having this unified data structure, deciding on ways to optimize how we do stuff. All of that has been really exciting and really innovative. In terms of what people at Cadent do next, I think that they've already started doing it. Already started looking at how they can make their data more available, storing it efficiently, and we've agreed, like, I know that it's been a lot of back and forth between the data owners, so we've basically kind of developed this methodology so that we have like pipelines ready for data moving forward.
Really encouraging data best practices, as well as further model development and deploying it at a wider scale.
Yeah.
Awesome. So Chris, same question. What do you think makes the DPLA project so innovative, and what are the key next steps?
Well, where to start? I think next steps, we've got to bolt all these different pieces together, because as we'll talk about in the series, there's the high pressure, the AGIs, there's the domains and services, connecting it all together in the platform, giving companies like Cadent and all the other partner gas networks in the UK and gas transmission a set of information that just helps us to make smarter, better decisions. But I think the next steps are bolting it together and really showing, as we've shown in individual cases like we talked about earlier, but showing that as a package, it connects up and it works and it's useful. And then working with the stakeholders to sort of step it into the real world. It's almost like I'm a father. Those kids, you help them at home, you start by feeding them one spoon at a time, but then one day you're watching them from a distance in the playground, and it's that as it steps away from us, it becomes more mature and it becomes more normal. And over the course of Rio 3, we expect to kind of both report our emissions in terms of the shrinkage and leakage model, which is the model that's the coefficient based, but also report using the DPLA about actual measured emissions, and we'll report them both. That'll be really interesting, and it'll be really interesting to see how all the industry stakeholders respond to that and what their views are, and about how we continue to kind of move it forward as an industry.
Okay, yeah, sounds like a really exciting time in the project and quite a critical one as well. So yeah, I hope everyone enjoyed hearing about the probabilistic modeling. Chris, Rubab, thank you so much for sharing your insights today. It was a really, really great and productive conversation. That concludes today's episode. And we've learned a lot about how the digital platform for leakage analytics is helping Cadent take a proactive and data-driven approach to reducing gas network leaks and emissions. Stay tuned for our next episode, where we'll be diving into the latest in-field methane detection technologies. Until then, keep following the journey of the DPLA project as we continue to explore new ways to make the gas distribution network smarter, safer, and more efficient. Thank you so much for listening.